Imagine your brain as a library where well read books sit proudly on the shelf, but if you never open a text for years, its pages yellow and the spine weakens. Eventually, it falls off the shelf unless you revisit it. Neuromorphic chips try to mimic this library with tiny synapse devices, like memristors, that hold information by their electrical conductance. But just as ink fades, these silicon synapses can slowly drift or forget their stored weight over time. Have you ever saved a document on a USB drive only to find it corrupted months later? Some membristors behave similarly. You program them to a certain conductance level, but tiny currents and heat cause that level to creep up or down over hours or days. Engineers call this drift, and it can erase learned patterns if left unchecked. Yet, could this drift actually be helpful? If you design it right, the chip can forget outdated data automatically, like clearing old calendar reminders so your schedule only highlights what's coming up next. What about devices that forget really fast? Enter phase change synapses, which store data by rearranging atoms in a chalcogenide glass. Under normal conditions, their structure slowly relaxes back toward its original state, causing the stored memory to fade in minutes or hours. Imagine writing notes in disappearing ink, perfect for short-term reminders. Remember to take out the trash, but not for your lifelong address. By tuning the material, designers can create both fleeting and lasting memories on the same chip. Could neuromorphic chips suffer actual circuit fatigue? Just as repeatedly crushing and uncrushing a paperclip eventually snaps it, every update cycle stresses a memristor's material. After millions of writes, some devices lose their ability to hold any weight at all, an endurance limit. To keep the network healthy, AI systems spread each memory across many synapses, like storing a single novel in dozens of tiny libraries, so the loss of a few copies doesn't ruin the story. So, is forgetting always a flaw? Not at all. It can make AI more adaptable. Question: why would we want our chips to forget? Because in a world where data streams and constantly holding onto every detail clutters the network, controlled forgetting, just like pruning old branches, helps neuromorphic systems focus on what matters now, improving learning speed and preventing information overload. In effect, neuromorphic fatigue and drift become tools to sculpt flexible, brain-like intelligence in silicon. Neuromorphic circuits are hardware systems designed to emulate the structure and dynamics of biological neural networks. Unlike traditional von Neumann architectures, these chips integrate memory and processing in interconnected arrays that resemble synapses and neurons. They operate using spiking signals, local plasticity rules, and parallel computation, often implemented through memristors, phase change materials, or analog CMOS devices. The goal is to replicate features of the brain, such as energy efficiency, adaptability, and real-time learning. However, because they are built from physical components, they are also subject to material degradation. Intel's Loihi chip uses event-driven spiking neurons and synaptic plasticity for real-time learning tasks. Neuromorphic chips are like synthetic brains sculpted from silicon, flexible, spiking, and low power. While software-based forgetting is intentional, e.g., weight decay dropout, neuromorphic hardware may exhibit unintentional forms of forgetting due to physical effects. Drift and resistance, charge leakage, and thermal noise can cause gradual degradation of stored synaptic weights. Memristive devices in particular may lose precision over repeated writes due to atomic migration and fatigue. Unlike static memory in digital systems, analog neuromorphic synapses can evolve or degrade naturally over time. This raises the question of whether forgetting is a bug or a feature to emulate biological aging. Memristors used as artificial synapses have shown conductance drift, leading to unstable network performance over weeks. It's like a chalkboard slowly fading, even if no one erases it. Just from exposure and time, in biological systems, neurons and synapses exhibit fatigue, reduced responsiveness after sustained activity due to ion depletion, neurotransmitter exhaustion, and homeostatic plasticity. Similarly, in neuromorphic systems, repeated firing or excessive updates can wear down materials, reduce signal fidelity, or alter device thresholds. These parallels suggest that long-term degradation in artificial synapses might approximate biological forgetting or synaptic pruning. However, artificial fatigue lacks the self-repair and adaptive recovery mechanisms seen in biology. Bridging this gap remains a key engineering challenge. Phase change synapses in IBM's True North chip exhibit programming fatigue after repeated learning cycles. It's like a violin string that loses tone after being played for hours. Until it's retuned or replaced, most neuromorphic devices rely on physical properties like resistive switching, memorist, ferroelectric polarization, or phase changes, which degrade over time. Tiny shifts in atomic structure, ion migration, or filament formation can cause non-ideal behavior like weight asymmetry, device-to-device variation, or long-term drift. These effects can mimic forgetting but may also destabilize learning, leading to unreliability in long-term tasks. Engineers must balance non-volatility and plasticity while mitigating fatigue through redundancy or adaptive algorithms. Understanding degradation is key for robust lifelong learning. In resistive RAM synapses, conductance can shift by 10-30% after a few 100,000 cycles. It's like a memory foam mattress that remembers less with every toss and turn. In brains, forgetting is often adaptive. It prunes unused pathways, avoids overfitting, and maintains learning flexibility. Similarly, controlled fatigue in neuromorphic systems could serve as a regularization mechanism, forcing networks to adapt or relearn. Stochastic decay could prevent local minima entrapment or simulate biological processes like sleep-based synaptic downscaling. Instead of error, forgetting becomes a tool for creative learning and memory consolidation. Research is exploring how forgetting circuits might enhance adaptability in artificial agents. Simulations using stochastic synaptic decay improve performance on continual learning tasks by mitigating catastrophic forgetting. It's like a gardener trimming a bonsai, removing just enough to let the tree grow better. To assess forgetting in neuromorphic chips, researchers track changes in synaptic weights, spike timing reliability, and output accuracy over time in training cycles. Experimental protocols include accelerated aging tests, noise injection, and periodic reevaluation under static and dynamic loads. Drift and fatigue are measured through metrics such as conductance, decay rate, retention time, and device hysteresis. Longitudinal data is essential for distinguishing beneficial plasticity from detrimental degradation. Hybrid hardware-software systems may use metaplasticity thresholds to adaptively recalibrate fading connections. In Loihi, researchers monitor synaptic health by comparing expected and actual spike-induced plasticity over days. It's like checking the ink in a pen, noticing that the lines fade as the cartridge dries. New neuromorphic architectures include redundancy, error correction, and noise-tolerant learning algorithms to overcome hardware fatigue. Some designs incorporate reconfigurable routing and homeostatic plasticity to shift learning to healthier regions of the chip. Others simulate biological mechanisms like synaptic tagging or neuromodulation to prioritize stable memories. A promising direction is integrating self-healing materials or analog refresh cycles to restore function. Forgetting becomes part of a feedback loop, not an endpoint. Adaptive spike timing plasticity rules in analog hardware allow networks to reroute around degraded synapses. It's like rerouting traffic when a bridge begins to wear without stopping the entire city. If neuromorphic chips can forget, age, and exhibit degradation-like behaviors, they may also help model cognitive decline, learning disabilities, or brain aging. Aging AIs could simulate progressive memory loss, enabling research into dementia or long-term neurodegeneration. Conversely, digital immortality may require wear-resistant, fatigue-proof substrates and memory protocols. Understanding forgetting in machines may mirror understanding memory in minds. The boundary between artificial decay and emergent cognition is a growing research frontier. Brain-inspired simulations of Alzheimer's have been conducted on neuromorphic platforms by degrading memory retention circuits over time. It's like watching a digital candle flicker, not because it's programmed to, but because its wax melts too. Neuromorphic chips do not merely compute. They evolve, adapt, and potentially forget like biological brains. Physical degradation, stochastic drift, and signal fatigue introduce challenges, but also opportunities to mimic the temporal fluidity of living cognition. By embracing forgetting as part of the system rather than a flaw, we may design machines that adapt, prune, and rewire as needed. Fatigue in neuromorphic systems may be more than wear. It may be synthetic memory's natural rhythm. The future of AI may lie not just in how machines learn, but in how they forget. A network that loses rarely used pathways, but retains essential memories, performs better in long-term autonomous tasks. It's like an artist forgetting old sketches to make space for a masterpiece yet to come.